Hello everyone and welcome to this Neptune CFD Stratified flow tutorial. It is a two-phase free surface flow inside a down corner. This tutorial is split into 4 cases in order to present different ways to handle boundary conditions and to define fields. A 5th case will be presented later to introduce the CRTS coupling with Neptune CFD. So first of all, you need to create a study, stratified flow. And in this study we are creating 4 cases, so with the -C option. Once it's done, you can go on the mesh directory and copy every meshes which is in the installation directory into this mesh directory. Then go on case 1 data and run the following command to open the graphical user interface. You now need to add the different meshes you just copied, so M1 and M2. Then click on preprocessing and add a face joining and let the following characteristics. Then on boundary zones, you need to add a water inlet with the selection criteria 5. Then an outlet. As it is a two-dimensional problem, all the faces normal to the Z component are symmetries. And all the other faces are defined as walls. Then click on Calculation Features and select the Eulerian multiphase Neptune CFD flow model and select the user defined. On main fields, change the field label as water and air. In this case, the energy isolation will be used for the water field. Then click on Turbulence Models and use a K-epsilon turbulence model for both fields. On body forces, add the gravity on the y-axis. Then on closure modeling, for the interaction between water and air, you can let the different properties as default. On volume conditions, check initialization and then go on all cells. Here both fields are defined as user material, so we can change the values. Let the temperature as it is. The water density will be calculated with the physical properties subroutine. So you just need to change the last 3 fields. For the air field, change the different values as follows. Then click on the initialization tab. For the pressure, put 70 bars. For the water field, initially there's no velocity. And for the volumic fraction, the user initialization will set the water height. For the thermal field, select enthalpy and set a value of 2 million joule per kilogram. Same thing for the air field, there's no velocity initially, and for the volumic fraction, the subroutine will set the water height. Now click on boundary conditions and set the different natures of the boundary conditions. For the water inlet boundary condition, click on water and put a volumic fraction of 1. Keep the velocity of 1 meter per second. And for the thermal field, let imposed enthalpy and set a value of 1,400,000 joule per kilogram. For the air field, you can let the default values. Now for the outlet boundary condition, set a reference pressure of 70 bars. And for the water field, set a volumic fraction of 1. You can then let the default values for the air field. And then for the walls, you can let a zero flux for the thermal field. Now for the numerical parameters, click on time settings and set an adaptive time step option with the time analysis of 20 seconds. On post-processing, click on the writer tab and set an output every X seconds and set the value of 0.2 seconds. Now in the monitoring points tab, add a probe with the following coordinates. You can choose the format at .csv or .dat. Once it's done, save your case. Then go back on your terminal window, go in your source directory, and add the user initialization and the user physical properties. Once it's done, go back on your graphical user interface and launch the simulation. Now let's post-process the results using PowerView software. On PowerView, we can display the water velocity and see its evolution. We can also see the water enthalpy evolution. For the case 2, an air inlet is added on the top of the domain to regulate the air-water stratification. You need to go into your case 2 directory and copy the setup.xml from the case 1 into your data directory. Same thing with the sources used in the case 1. Then go in your data directory and launch the graphical user interface. In this case, you need to add a boundary zone. So click on Add. The label is Air Inlet. And the selection criteria is 14. So you need to withdraw 14 from walls. Then go on boundary conditions and change the air inlet nature into inlet. Then click on air inlet. For the water field, no need to change anything because there is no water in the air inlet. And for the air field, set a volumic fraction of 1, and the mass flow rate will be defined as a function of time in the C user routine, the user boundary conditions. So you can set a very high value to be sure that the subroutine is taken into account. Once it's done, you can save your simulation and go back in your terminal window. In the source directory, We have already copied the user initialization and the user physical properties from the case 1. We now need to copy the last subroutine, which is user boundary conditions. You can then display the NC user boundary conditions. You can see the different parameters used in the subroutine. And the part which is important is at the end. You can see here that this is the name given at the air inlet. So you have to make sure this is the same one as in the graphical user interface. Then go back in your graphical user interface and then you can launch the simulation. We can now post-process the results with ParaView. We can display the volumic fraction of water and see its evolution. And same thing with the water enthalpy. Some outputs have been made in the listing file to compare the profile of the theoretical water level in the down corner with the simulated water level. By executing this command, only the values will be set in an external file. And using this Python script, you can plot the theoretical and the CFD values. So type Python with the name of the Python script. We can notice that the simulated level of water in the down corner follows the theoretical one with a small delay. Now, for the case 3, we will replace the air inlet with a steam inlet. So go on your case 3 directory and copy the setup.xml from the case 2 into your data directory. Same thing with the sources. Copy the NC user initialization in your source directory and the NC user boundary conditions from the case 2. Then to launch the graphical user interface, go into your data directory and execute the command Neptune CFD. First, you need to go on boundary zones and change the air inlet into steam inlet for the label. Then on calculation features, change the Eulerian multiphase from user-defined to stratified flow. It will reset your multiphase modeling choices and activate heat and mass transfer. On main fields, change the field labels for water and steam. The energy resolution is activated automatically. On turbulence models, let K epsilon for both fields. And for the continuous phase coupling, choose separate phases. Then click on closure modeling. All the setup is automatically set. Click on interfacial enthalpy transfer and on wall transfer parameters. Even though the models are already set up, you need to click on the different tabs to activate the models. Then click on all cells, and for the material, choose water to activate the Cathar method. Then click on the initialization tab. For the pressure, let 70 bars. And then for the steam field, initially there's no velocity. Put a fraction of 0. And for the thermal option, choose saturation enthalpy. For the water field, For the temperature, choose a value of 500 kelvins. And initially there's no velocity, and for the volumic fraction choose 1. On boundary conditions, for the water inlet, in the water field you just need to change the thermal properties into temperature, and for the steam you just need to change the thermal properties into saturation enthalpy. For the outlet, the default values for both fields are good. And then on steam inlet, for the water field, no need to change anything. And for the steam field, let a very high value for the velocity to be sure that the NC user boundary conditions is taken into account. And choose a saturation enthalpy. Then save your simulation. And go into your source directory, edit the NC user boundary conditions, and here you need to replace air inlet with steam inlet. Then go back into your graphical user interface and you can launch the simulation. For the post-processing, so you can display the volumic fraction of water, or the water velocity. You can do the same thing as before to plot the water level for the theoretical and the CFD values. We can notice that the simulated level of water is overestimated when the steam injection is important. For the case 4, the steam inlet will be replaced by a free outlet with pressure regulation. You need to go on your case 4 directory and copy the setup.xml from the case 2 into your data directory. Then copy the NC user initialization subroutine from the case 2 into your source directory. And same for the NC user physical properties from the case 2. Then launch your graphical user interface. So you need to go on boundary zones and change the air inlet by your air outlet. The selection criteria remains 14. Then click on boundary conditions and change the air outlet nature. Click on the air outlet boundary conditions, and for the water field and for the reference pressure set a very high value to be sure that the routine is taken into account. And for the air field, change the volumic fraction to 1. You can then save your simulation. Then go into your source directory. You need to copy the NC user boundary conditions from the installation directory where the tutorial files are present. If you open that subroutine, you can check if the name of the boundary condition is the same as in the graphical user interface, so air outlet. Then go back in your data directory and launch the graphical user interface. So you can launch the simulation. You can then open ParaView to post-process the results. So you can see the evolution of the volumic fraction of water. As for the other cases, we can plot the water level for the theoretical and the CFD values. For this case, we can see that the level of water is oscillating around the theoretical water level. A fifth case will be created, built from the case 3. The objective of this case is to study the influence of the heat transfer through a couplet calculation with Sirtes. So go back in your tutorials directory and create a new study, Stratified Flow Sirtes, -C, the case name for the CFD study, and then -- Sirtes equal the study name for the Sirtes study. It creates a case 5 directory for the Neptune CFD case and a Sirtes directory for the Sirtes case. So first of all, you need to copy all the mesh from the installation directory in your mesh directory. Then copy the setup.xml from the third case into your data directory. Same thing with the sources. You need to copy the NC user boundary conditions from the third case. And the NC user initialization. Then go on data and launch the graphical user interface. You need to go on the boundary zones tab and add a new boundary regions. This will be the couplet wall with the selection criteria 15. So you need to withdraw 15 from the walls selection criteria. Then go on your CHT wall boundary conditions and change the thermal properties from flux to Sirtes coupling. And you need to set the Sirtes case name, which is Sirtes. And you can see on the coupling parameters tab that the Sirtes coupling is taken into account. Then go into your Sirtes directory. You need to source the Sirtes environment. Then launch the following command, sirtes.guy. Once the Sirtes guy is opened, you need to click on New Data File. The dimension of the problem is 3D. And don't forget to check conjugate heat transfer. Then on file names, you need to add your mesh into the conduction mesh. You can set a file with the extension MSH. It will be automatically converted into a SYR file. Then on initial conditions, set a temperature of 1000 degrees. Be careful, here the unity is Celsius. For the references, you have to set -1 to select all the domain. Now in boundary conditions, go in the flux condition tab and set a flux of 0 with the reference 2. On physical properties, set the following values with the reference -1. Now on conjugate heat transfer, you need to write the name of the Neptune CFD case, in that case, case 5, with the reference 1. Now on the control panel, set a global number of time steps of a very high value, so the stopping criteria comes from Neptune CFD, and set a value of 1 millisecond. Even though the field is in red, the value 0.001 is good. Now on output, go in the result fields tab and check 3D fields and set an output every 0.2 seconds. Then save your file into the name Certes data. Then go back into the study directory. Then execute the executable Neptune CFD with the file run cfg. It opens a graphical user interface to set up the number of processes for the Neptune CFD case and the Certes calculation. And then to be able to post-process the Certes results, in the OPT field, you need to set -v ENS for Insight. Into the param field, you need to set the Certes file name you saved. Then save this file. You can check the different parameters by displaying the run.sfg file. Then to launch the computation, you need to be in the study directory and execute the Neptune CFD command with the run option. If you opened a new terminal, don't forget to source the Certes environment. Then you can see on the residue coupling directory that the results are divided into two directories, the Neptune CFD1 and the Certes one. Then you can open PowerView to post-process the results. You can display the volumic fraction of water. Then we can display the temperature. Don't forget that for the Neptune CFD results, the temperature is set in Kelvin, and that for the Certes results, it's set in Celsius.